This is lesson 2 for chapter 11, calorimetry. You can break the word down. We have the word calorie and metry, of course, meaning metric, measuring calories. Obviously, this word was around before everyone pretty much switched over to joules as far as being the unit of heat energy is concerned. Now, you've used calorimeters before. Typically, we've used a styrofoam cup inside a larger styrofoam cup holder. And so the two kinds of styrofoam side by side really help to limit any loss of heat or gain of heat from the environment, sideways at least. And then we had a cap that we could put over the top, and that's not quite as effective as the sides were. But we still got pretty decent results back in chemistry when we did some experiments with calorimetry. The equation right here, heat, that is the thing that is hot is going to lose heat, and so this negative sign tells us it's exothermic. And this positive sign here tells us this is endothermic. It's going to gain the heat. Another way that I like to do it is I like to say that the heat lost equals the heat gained. And then I take care of this negative sign because of the exothermicity in a way that you'll see in just a few minutes. So it makes my calculations a little bit easier. It's up to you if you want to use my method. And again, I'll show you that in just a minute. So if we look at this problem, we have a 125 gram block of an unknown substance with a temperature, it's in a container of hot water probably at 90 degrees Celsius. And then we take that hot piece of metal and we put it into a styrofoam cup that's got water in it, and the water is at 20 degrees. So if you think of the 90 degree temperature for the metal and the 20 degree temperature for the water, obviously the final temperature is going to have to be somewhere in between, and we're told that that final temperature is 22.4 degrees Celsius. So the metal is going to be losing heat, and the water in the calorimeter is going to be gaining heat, and it looks like we are ignoring the specific heat of the calorimeter itself. If we were worried about the specific heat of the calorimeter, we would have an MC delta T for the calorimeter right here, because the calorimeter and the water would have exactly the same temperature to start with and the same temperature to end with. But since we're ignoring any heat gained or lost by the calorimeter, I'm just going to get rid of that and come back to the simplified problem. Now, the way I would set up the problem is like this. Heat lost equals heat gained. So I'd have the MC delta T for the metal losing heat and the MC delta T for the water gaining heat. But in both cases, I would make my delta T an absolute value. In other words, for the metal, I would take my initial temperature, which is the higher temperature, minus the final temperature, the 22.4. That would be my delta T. And over here for the water, I would take my final temperature, 22.4, and then my initial temperature, so that in both cases I would get a positive delta T. And that way this negative number here, because remember the negative times a negative is going to give me a positive number. And so that's why my method can work, because I'm taking the absolute value of both temperatures, which allows me to ignore the negative sign in front of the thing that is losing heat. So anyway, I'm going to move on to the next problem. which is going to be a little bit harder, meaning a little bit more interesting. So we have 4 kilograms of water. At 40 degrees Celsius, it's poured into a glass speaker that has a colder temperature, and then we have a block of aluminum that's at 37 degrees. So you notice we've got 3 different temperatures here. They set up a nice table to show you everything. And the summation of all the heat must equal 0. The way that I would set up is everything that's losing heat must equal everything that's gaining heat. And then I would just have the absolute values for all of my delta T's. That method will work as well. In any case, when they solve this problem, they don't tell you the fact that this number and this number and this number are actually the mass times the specific heat. The mass times the specific heat. And then this part here is the delta T. So you have the Q equals MC delta T for the water, the Q equals MC delta T for the aluminum, the Q equals MC delta T for the glass. And then they separate out the temperature. They divide the temperature out all the way through, or use the associative property, I guess. And then they solve this equation for the temperature. And the temperature comes out to be 37.8 degrees. Now, besides causing a change in temperature, heat can also cause a change in state. And the word latent is a word that in general vocabulary means hidden. Hidden. Maybe you had it in one of your vocabulary word note cards. Sometimes in forensic science we talk about a latent fingerprint. So you look on a smooth surface or maybe a glass at the crime scene and you don't see any fingerprints until you dust it with powder. And then now you can see those fingerprints. The fingerprints were latent or hidden until you revealed them by dusting with the powder. And I've done this on numerous occasions in the forensic science class that I used to teach. The students actually did it in the lab. It's a lot of fun. So here we're going to be talking about a phase change. And the reason we use the word latent is because here you are adding heat to something, and let's say the thermometer is in it, like water or whatever, or maybe a block of ice or something. But as you're adding heat, the temperature doesn't change. Well, if the temperature's not changing, where's the heat going? What's the heat doing? And it's actually causing a change in state. And you don't necessarily observe the change in state, solid to liquid, liquid to gas, or vice versa, right off the bat, while it's changing state. And therefore we call it the latent heat. The latent heats go with the phase changes. And it's the same latent heat to go from solid to liquid as it is to go from liquid to solid. And it's the same latent heat per gram, that it takes to go from liquid to gas or gas to liquid. Now we use an old-fashioned word for solid to liquid or liquid to solid, and that's the latent heat of fusion. Fusion was an old-fashioned idea of a liquid coming together in such a way to become a solid. Fusing has nothing to do with nuclear fusion, the way in which stars produce their energy. And whether you are vaporizing or condensing, we call this the latent heat of vaporization. So we have our L sub F and our L sub V for these two latent heats. And you can see the chart, and once more, you'll notice that water has the largest or near the largest latent heat of fusion and latent heat of vaporization of certainly of any of your gases or other liquids, and it's even greater than some of your other solids. And again, those hydrogen bonds are responsible for an awful lot of the unusual properties that water has. So this is the chart, and of course on an AP test, all these values, just like all the values of specific heats, will be given to you. You would never need to memorize them, though the most common latent heats are, of course, the ones for water. Now, if we were to make a graph of a beaker of water, or let's say it's ice, and we had a thermometer sticking in there, and let's say that my beaker was sitting on a tripod, and there was a little Bunsen burner, and there was a flame heating up this block of ice, and let's say that this ice began at a cold temperature below the freezing point. Let's say the ice started off at minus 30. And as we heated it up, the temperature went up. But at 0 degrees, the temperature stopped going up, even though we're still adding heat. In other words, it plateaus, and that's where you have your phase change. So your phase change is in section B. But then when all of the ice is melted, which means that any mixture of ice and water is 0 degrees at ordinary pressure, standard pressure. At 0 degrees, when all of the ice is turned into water, now we're in part C, and now we have a temperature change. But that temperature change stops at 100. Because at 100 degrees, it's starting to turn into steam. And so this water is absorbing heat, absorbing heat, absorbing heat until the steam begins to form. And then you can have a higher temperature of steam. And steam can be very, very hot. If you're confronted by Al-Qaeda and they offer you two options, to have boiling water put on you at 100 degrees or steam at 100 degrees, take the boiling water, because the steam has the additional latent heat of vaporization added to it. Now, of course, that's not entirely true, because Al-Qaeda doesn't go walking around with boiling water and sources of steam, at least not in my experience. But also, of course, the boiling water would be much more concentrated than the hot steam, and but you get the point, hopefully. Now, this is what I call a 5-step problem. 5-step problems, because you have 5 places where you've got to find the heat. You've got part here, part A, you've got part C, and you've got this part at the end, part E, all of which are MC delta T. So part A is an MC delta T, part C is an MC delta T, and part E is an MC delta T, because you have a change in temperature. Please note that your specific heat for steam is different than the specific heat for ice and water and steam. They're different, not the same thing. In the other two cases, and I'm going to erase some of the mess here. In the other two cases, in part B and in part D, you have a phase change. So in the phase change, go to a different color. In a phase change, you've got your heat equals your mass times the latent heat of fusion, and your heat times the latent heat of vaporization. So these are your 5 steps. Steps 1, 2, 3, 4, 5, or A, B, C, D, E, as you can see. Make sure also that you remember that your latent heat of fusion is different than the latent heat of vaporization. Make sure that your temperature change is only, when it comes to the ice, to go from minus 30 up to 0. And then from water, you're going from 0 up to 100. And then for your steam, in this particular problem, you're going from 100 degrees up to 120 degrees, which is why that delta T is 20. Then, of course, the last thing you need to do is add all 5 steps up to get the total amount of heat that it takes to go from minus 30 all the way up to 120 for this particular mass of ice that later became water, that later became steam. And it should tell us somewhere what that mass was. It looks to be about a gram, 1 times 10 to the minus third kilograms. One other thing I should mention, just noticed it, by far and away, the most energy is involved in the phase change of water to steam. The area under the graph is the total amount of energy involved in that particular part of the process. So let's take another look at another problem. At a party, you got 6 kilograms of ice at minus 5. And you're adding it to a cooler that's got 30 liters of water at 20 degrees. In fact, if you had sugar water, flavored water, you could be making your own soda pop. And in this problem, the first thing we need to do is find out what is our mass of water. And so you'll notice we take our density times volume to get the mass of water, coming, of course, from the definition that density is mass per volume. Once we know the mass of water, we can now do our stoichiometry, because, I should say the mass of the ice, because we're going to raise the temperature of the ice, then we've got to melt the ice, and then that becomes ice water, and then the ice water is going to go up in temperature all the way to 20 degrees. So we've got to go from minus 5 to 0. That's a delta T change. Then from here to here, we have a phase change. Latent heat of fusion will be involved. And then from here to here, there's another delta T. Every time you have a delta T, Q equals MC delta T. Every time you have a phase change, mass times the phase change. And so all we're doing is just adding these heats up. Let's see if I make sure I covered everything correctly. Let's look at this problem here. 5 kilogram block of ice at 0 degrees. We're adding it to an insulated container that's partially filled with 10 kilograms of water at 15 degrees. And we're told that there's going to be some ice that will, some of the ice is going to melt, which means some of the ice is not going to melt. If we make a diagram of our graph, just a little bit, up, over, and up. What we have to worry about is our ice is starting off at 0 degrees, which is right there before it melts. And then my ice has got to melt. So if I change colors here, my ice has got to melt, and then it's got to go up in temperature. Meanwhile, my water that is in the insulated container is going to be at 15 degrees, and it's going to come down. So you can see from my the 2 green arrows, let's come back to green again. I have gaining heat, 1, 2, and the purple is losing heat. Heat lost equals heat gained, and this little map helps me to keep track of how many terms I'm going to need. I'm going to need to melt the ice, and then I'm going to need to raise the temperature. of that ice water now. Meanwhile, the temperature that's already in the insulated container has to come down. So it looks like this goes with that. And oh, I see what we're doing. We are actually doing the ideal and the actual. If we were to melt all 5 kilograms, it would take this much heat. For my water to come down to 0 degrees, MC delta T, it's going to take this much heat. Obviously, this much heat is much less than this much heat if you look at the powers of 10. So I don't have enough warm water to melt all the ice. So I'll take the heat that I do have, put it down here, and melt M amount of ice with that heat. And I'm only going to melt 1.89 kilograms of it. And so that means 5 minus 1.89 is going to be the amount of ice that is left. And the last problem is about Armageddon. And it's kind of funny to read this problem because you've got all of these assumptions. Not only are there assumptions, but they say things like contrary to fact. And the law really doesn't apply. But of course, this is physics, and we can make all kinds of estimates and come up with reasonable answers that maybe get us in the ballpark. So the first part, of course, is we got to find out what is the mass of ice in my comet. And then that comet is going to melt, and then it's going to increase in temperature until it turns into steam, and then it's superheated steam. So we've got these 4 terms. 2 of them are phase changes, and 2 of them are MC delta T's. Plus we have the overall kinetic energy of all of these particles moving around. In other words, what we're doing is we are, if I can blow this up here a little bit, we are setting the MC delta T equaling to the kinetic energy that we can get from all of that energy stored in the comet as it turns into steam. As my comet is turning into steam, we have particles, high energy water molecules with a lot of kinetic energy. Notice that the masses cancel out. So we don't actually need to know, for this part of the problem, the mass of the comet. And we can find the temperature. Of this superheated steam. We can also plug this into PV equals NERT once we take our mass of the comet and convert it into moles of water. This is going to be the letter N. Plug that into PV equals NERT, and we can find the pressure. And of course, this pressure, they tell you here, is a pressure many, many times greater than the pressure it takes to break a band of steel. And it would also cause all kinds of problems like fires and tidal waves and wiping out the coastal regions. The sun would be obscured maybe for 10 years. And maybe Homo sapiens sapiens, that would be us, might become extinct. So if you really got to worry about something, worry about this. Don't worry about Al-Qaeda. Don't worry about COVID. Worry about those errant comets that are threatening mankind. By the way, we're keeping track of them, and we can always send Bruce Willis up in a rocket ship to blow one up if necessary.